We're going to today talk about inverse functions. Remember last time we talked about composition of two functions. We're going to do a special type of composition today in order to explain, understand, and learn the significance and the application of inverse functions. Think about a nice situation. Say you have a function with the domain of the function df. The function takes you from the domain to the range of the function, which I'm going to call the set Rf. I said think about a nice situation because I wanted to make sure that I can devise an inverse rule that will bring me back from the set Rf to the set df. And what we'll essentially call this inverse rule is the inverse of the function f inverse. So I'm writing f to the power negative 1, but I will remember that f to the power negative 1 is not 1 over f. In the context, if f is a function, then we will understand f to the power negative 1 will be read as f inverse and will be defined in a certain way so that if I compose f and f inverse, I will get back the input variable x. Let me explain that a little bit in detail. Say x is a point in the domain of the function f. Then you know that this being the input, the output is going to be fx. What is the inverse function? The inverse function takes the output for x under f and gives you back x under the composition of functions. So if I do f first and then I repeat the application of f inverse over the output of f for the input x, I get back the input x. So f inverse composed f always gives you back the input. Not only that, this process must be true if I change the order of implementation of the function and its inverse. So f composed, f inverse of x must give me back the input x as well. How do I ensure that this nice situation is happening? In order to make sure that this nice situation is happening, I have to introduce a new concept, which is one-one-ness or injectiveness for a function. So if my function is 1-1 or injective, then I get to say that f inverse exists. So I will write that if f is injective or 1-1, then f inverse exists. So what is this one-one-ness or injectiveness? If for every output of f in the range of f, there is precisely or exactly one input, then f is called injective or 1-1. So we'll give you a couple of examples. First and foremost, think about the function which is described as in the form of ordered pairs. For example, say it is 1 comma 2, that means 1 goes to 2, 1 is the input, 2 is the output, and then I will write down one more ordered pair of this nature, say 2 comma 5 and say 3 comma 6. So if I want to consider the domain of this relationship, then the domain are 1, 2 and 3. What will be the outputs set? That's the range, and the outputs are going to be 2, 5 and 6. What I want to ensure is if I consider any output, so see 2 is an output, and for 2 there is exactly one input. Similarly, if 5 is your output, there is exactly one input. If 6 is your output, there is exactly one input. So this relationship is a function which is 1, 1. So let's talk about an example where the relationship might not be 1, 1 or injective. For example, let's take the same set of points 1, 2, 2, 5, 3, 6, and in addition, I take 4, 6. Think about it. This is a function. There is no question about it. If I consider the domain set, it's 1, 2, 3, and 6. Is 4. 1, 2, 3, and 4 are the inputs in this relationship. 1, 2, 3, and 4. Let's consider the output set. Output set are going to be 2, 5, and 6. See, I have one more output, but that is 6, so I'm not going to repeat that. If you think whether this is a function or not, then you will see 1 is going to precisely to 2. There is no different output for 1. There is exactly one output for 1. 2, there is exactly one output for 2. 3, there is exactly one output for 3, and that is 6. How about 4? 4 also has exactly one output, and that is 6. But if I think about how about the outputs and try to count the inputs, I will see 2 has exactly one input, 5 has exactly one input, 6 whereas has 2 different inputs. So even though this relationship is a function, it is not 1, 1 or injective. Why it is not 1, 1 or injective? Because I can think of one output 6 that has more than one inputs. 6 as an output has more than one inputs. So it is not 1, 1 or injective. Hence, I cannot talk about the inverse function for this relationship. Given a function in the algebraic form, we will devise ways in order to understand whether the function is 1, 1 or injective or not. So I will call it algebraic checking for 1-1ness or injectivity. Say you are given with a function fx and you want to know whether it is 1, 1 or not. So I will put a question mark because I want to check whether this is 1, 1 or not. How do I check it? Start by assuming you have exactly one output for two different inputs. For example, f for the input A should give me the input B. Then try to establish A equal to B by doing your mathematical manipulation. If you are successful in doing so, f is 1 to 1 or injective. And I will show you real examples, and this process will make way better sense for us. There is one graphical approach in order to understand one-oneness or injectivity for functions. So I'm just going to call it graphical approach. Remember what we did graphically in order to understand whether you were a function or not? That was vertical line test. We were checking whether one input has multiple output, or vertical line test. For the graph, if you have a line, a vertical line crossing the graph in more than 1 points, then it is not a function. So this was for checking whether you were a function. As we have seen, you can be a function, but at the same time, you might not be one function. So what is the check? The check is horizontal line test. And it is essentially going to check whether I have two different inputs giving me the same output or the same height sitting on the horizontal line. Or in other words, if one can find a horizontal line, so remember horizontal line represents the height that crosses the graph in more than 1 points, then the function is not 1 or injective. And I need to do all these work, all these extra work in order to understand whether we can talk about the inverse of a function or not. So I think we are in a pretty good shape, and I'm just going to remind you one more time what it means to be inverse. If I compose the function f with its inverse, doesn't matter from which direction you are doing it, your answer should just be the input x. That's how we are going to check whether two functions are inverses of each other or not. How do I check whether the function is 1 or not? We just found out that there are two different approaches in order to understand whether the functions are 1 or not. Given the algebraic form, start by saying f at input A is equal to f at input B. If you can establish that A is equal to B, then you are injective. If you cannot, you are not injective. Graphically, if you can find a horizontal line that crosses the graph of the function in more than 1 points, then the function is not 1-to-1 or injective. If a function is injective, then it has inverse. So what does the inverse do? Inverse of a function interchanges x and y coordinates. What do I mean by that? Think of an 1 function. For example, let's talk about 1, 2, 2, 5, and 3, 6. We have established that this is 1-to-1 function. So if you call this function f, then the inverse of the function is going to interchange or switch your x and y coordinates. So the inverse function will be given by 2, 1. So that whatever was the output is now the input, and whatever was the input is now the output. 5, 2, 6, 3. When I switch around all the x and y coordinates, I get the inverse of the function. So graphically speaking, the inverse function has a graph which is a reflection of the graph of fx along the y equal to x line. Let's try to do some of the exercises that we have been given in this handout, and hopefully they will make better sense for us and we will learn inverse function better. So I'm going to skip the definition and I'm going to go first blindly finding the inverse rule for a given rule. So for all these examples that we're going to work out now, I'm going to assume that your functions are already 1, 1 and hence they have inverse. So what is the process? First, replace the fx by y, then interchange between x and y, solve for y, and replace y with f inverse x in order to get the explicit expression for the inverse function. So let's do problems. I want to know the inverse of fx when fx is 2x minus 3. What I do first, I say fx is y. Then remember, inverse means you are interchanging between your x and y. So write it x equal to 2y minus 3. This is a linear equation in terms of y and you are supposed to solve it for y. So I add 3 on both sides. I get x plus 3 equal to 2y and then I divide both sides by 2. So y is now by itself, y is equal to x plus 3 over 2. Finally, I call y as f inverse x, which is x plus 3 over 2. And that will answer my question for finding the inverse of the function fx equal to 2x minus 3. And remember, at this point, we're not talking about the domain, and we're absolutely going to be extremely careful about the domains of the function and the inverse of the function when we're talking about inverses of function. But let's just skip the intricacy, just talk about the algebra of finding the inverse of a function. My next function is fx equal to cube root of x minus 1. I do the same thing. I say y equal to cube root of x minus 1, interchange between x and y. So x is equal to cube root of y minus 1. I'm trying to find the inverse, so I'm going to add 1 to both sides so that I can isolate y. And I will get x plus 1 is equal to cube root of y, and then solve for y. How do I solve for y? Remember our other algebraic equation? Because you have the cube root, you're going to take the third power on both sides. So the third power on both sides so that you get y by itself. So I get x plus 1 raise it to the power 3 equal to cube root of y raise it to the power 3. And I get y equal to explicitly solved for x plus 1 whole to the power 3. Final step, you replace your y by f inverse x, and that is equal to x plus 1 whole to the power 3. The next example is finding the inverse of the function y equal to fx equal to 2 minus 2x over 8 minus 3x. So what we will do, instead of using this hint, so I'm going to just black it out, and we're going to start talking about finding the inverse. So remember your processes, you're going to replace y by fx by y, so y is equal to 2 minus 2x over 8 minus 3x. Replace your x's and y's, interchange between them. So y becomes x, and every single x becomes y. So 2 minus 2, y, over 8 minus 3y. You are solving for x. What is the easiest process of solving for x? Well, look at the denominator and multiply that on both sides. And I want to do it so that on the right hand side, I can cancel the same factor from top and bottom. So I don't have any more denominators anymore. On the left hand side, distribute x. You get 8x minus 3yx equal to 2 minus 2y. Remember, the denominator got cancelled. I want to solve it for y. So let's gather all the y terms together. What do I mean by that? I add 2y on both sides. The other side, gather around your x terms, so subtract 8x from both sides and see what happens. See, they are cancelled. You have 2y positive minus 3yx equal to, the two y's are cancelled from right hand side, and you have 2 minus 8x. I see that both of these terms, they have y in common, so why don't I factor it out? And I will get 2 minus 3x equal to 2 minus 8x. Since I'm solving for y, I would like to divide both sides by 2 minus 3x. So y becomes 2 minus 8x over 2 minus 3x. I've solved it for y, so I will write down the last step of my problem, replacing y by f inverse x. And so f inverse x is 2 minus 8x over 2 minus 3x. So as you can probably imagine now, the process of finding inverse for a function is pretty mechanical. You just follow through the 4 steps, changing fx by y, interchanging variables x and y, solving for y, and finally replacing y by f inverse x. Let's go to page number 2 of our problems. Again, you are trying to find out what is f inverse of negative 3. So I will do this problem a little differently. What do I mean by that? Remember the nice relationship between f and f inverse. If I go back to the first slide, you will see that if f of negative 3, if negative 3, f inverse of negative 3. So what do I mean by that? This is f inverse, taking back negative 3 to something, is equal to a. So I'm saying if f inverse of negative 3 is equal to a, then if I do f on a, I should get back negative 3. So f of a must be equal to negative 3. That will be my point of understanding in order to solve this problem. So let's go back to the problem. We have f inverse of negative 3. Let's call it a. Then f of a is equal to negative 3. So what is f of a? Look at your f of x. So f of a is equal to a plus 1 over a plus 6. That should be equal to negative 3, and then you solve for a. How do I solve it for a? Well, we're going to multiply the equation a plus 1 over a plus 6 equal to negative 3 on both sides by the denominator a plus 6, so that the same factor from top and bottom cancels and I don't have any more denominators. What I get a plus 1 equal to negative 3a minus 18. Subtract 1 from both sides. You get a equal to minus 3a minus 19. But you are solving for a, so why don't we add 3a on both sides to get the a terms all on one side. So I get 4a equal to negative 19. Then I divide both sides by 4. I get a equal to negative 19 over 4. And remember what was a? A was f inverse of negative 3, which I wanted to know. So I will go ahead and say that f inverse of negative 3 is equal to negative 19 over 4. I hope that makes sense. You can also think of this problem in a little different way, which I'm going to do in a separate page. I have been given that fx is equal to x plus 1 over x plus 6. So what I can first do, I can find f inverse of x. How do I do that? I replace fx by y. So y is equal to x plus 1 over x plus 6. Step 2 is interchange between x and y variables. So x is equal to y plus 1 over y plus 6. Then in order to solve it for y, in step 3, I multiply both sides by y plus 6. The same factors y plus 6 and y plus 6 on the right hand side. From top and bottom, you cancel them, no denominators. On the right hand side, you have no y plus 6. On the left hand side, you start distributing. You get yx plus 6x equal to y plus 1. I'm solving for y. So get the y terms on one side, everything else on the other side. So I get yx minus y equal to 1 minus 6x. Y is common. Factor it out. You get x minus 1 equal to 1 minus 6x. To solve for y explicitly, you divide both sides by x minus 1. So you get y equal to 1 minus 6x over x minus 1. Remember the final step, your f inverse of x is equal to 1 minus 6x over x minus 1. I want to know how much is f inverse of negative 3. So negative 3 is my input. Why don't I go ahead and substitute x by negative 3. So see, on the top you get 1 plus 18. Negative times negative is a positive. On the bottom you have negative 4. So you get 19 over negative 4, which you know you can write as minus 19 over 4. And that was the answer in the previous way. So you pick which way you want to solve the problem, and you have multiple ways to answer the question. Let's go back to page number 6 and try to solve the rest of the problems. So it is talking about how the graphs of the function and the inverse function are related. If I give you the function, reflect the function's graph. So this one is the graph of the function. Reflect this graph along the line y equal to x to get the graph of f inverse. So if this is your f, this is your f inverse of x. So let's try to answer simple questions. The function is given by 2, negative 3, 4, 2, and negative 1, 5. We are interested in learning what is the inverse of this function. Remember the interchange between x and y. So you write it as negative 3, 2, 2, 4, 5, negative 1, and what you have is the inverse relationship of the given relationship. Let's fill in the blank questions. One-to-one function, different inputs always have different outputs. If a function is one-to-one, then the function has inverse. So remember this. In order to establish the inverse of a function, the original function must be one-to-one. The range of f inverse, which is the y values for f inverse, must be the x values for the function. So the domain of f is the range of f inverse. Whereas the domain of f inverse, so the x values for f inverse must be the y values for f. So the range of f is the domain of f inverse. A function that is increasing over the domain or decreasing over the domain is also one-to-one. So that's a nice nature. We know increasing function and decreasing function. If you are increasing or decreasing over the entire domain, now and so on, we will know that those functions are going to be one-to-one. Horizontal line test, we talked about it. If there is a horizontal line that crosses the graph of a function in more than one point, then the function is not one-to-one. See the parabola on the left. I can have multiple horizontal lines that will cross the graph in more than one point. So it is not one-to-one. Whereas the next picture is a picture for the cube root function. And as you can imagine, for this function, doesn't matter where you want to draw the line, it is going to cross the graph at most one point. So the function is going to be one-to-one. Let's go to next page, page number 8. We are finding the inverse for fx equal to x squared minus 1 when x is less equal to 0. Now this is a very nice problem. It is going to talk about the domain a little bit. Think about the function fx equal to x squared minus 1. Fx equal to x squared minus 1. It is the graph of x squared shifted 1 unit down. Shift fx equal to x squared 1 unit down. So how the graph is going to look like? So this is 1, it will be this parabola. But then I look at my original function, and the function is fx equal to x square minus 1. I have restricted all my x's to be less than or equal to 0. So I'm on the left hand side. There is no branch of the graph on the right hand side. Why I needed that? See, as you see the graph of fx equal to x square minus 1, if you do the horizontal line test, the function is not one-to-one because it is crossing the graph in more than one points. But now let's try to think about the graph whenever my x's are only less or equal to 0. So I don't have the right hand branch. See what happens. So if I'm considering only the left hand side, x less equal to 0, then this is the picture of the graph. Now do the horizontal line test, and you will see you are crossing the graph in exactly one point. So in order to talk about the inverse of a function which is not necessarily one-to-one, I restricted the domain and made it one-to-one so that I can talk about the inverse of the function. So now the process is pretty simple. It's the algebraic process. You're going to look at your fx and you are going to replace fx by y. So y is x squared minus 1. Then you are interchanging variables. So x is y squared minus 1. You want to solve it for y, so add 1 on both sides. You get x plus 1 equal to y squared. Now I will solve it for y by taking the square root on both sides. Remember, square root of y squared is absolute value of y, and I will get square root of x plus 1. So I get two solutions. I get y equal to square root of x plus 1, or I get y equal to negative square root of x plus 1. Which one is my right inverse function? The correct inverse function, which will be which one of these two? Well, also remember the graph of the inverse function is going to be a reflection of the original graph. So the original graph is on the picture. Draw the line y equal to x and reflect this graph. What will happen when I'm reflecting this graph? This point, which is the point negative 1, actually I'm going to make it a little easier to understand. I don't even have to know that. What is the exact value? I mean, you can find it. You can think that this is the x-intercept. So you can set x squared minus 1 equal to 0. So x squared is equal to 1. Take the square root on both sides. So you get absolute value of x is 1. So x is positive 1 or x is negative 1. But because I'm talking about this point, it is on the negative side. Your point is x equal to negative 1. That's why I started saying negative 1 comma 0. So the negative 1 comma 0 in the inverse function, your x and y coordinates are going to switch, and what you will end up having is 0 comma negative 1, which is the y-intercept. If you think about the y-intercept of this function, you set x equal to 0 and you will get 0 squared minus 1, which is negative 1. So 0 comma negative 1 is this point. So this point becomes this point. Similarly, this point becomes this point, and I will get the reflection as this blue graph. Now think about the range of this blue function. The highest point on the blue function is 0. This is the highest point. The lowest point can be any negative number. So it will go to negative infinity. So this is the range of the blue function. Means you are always non-positive. So your f inverse, which is the blue graph, is a non-positive function. Where I'm going to use that? Look at the two expressions I found for y. This one is always positive or non-negative. But for my problem, I found the inverse to be non-positive, which is this one. So I will say the correct inverse that I wanted to find for my function is the non-positive branch. And hence I'm going to go ahead and say that f inverse of x is equal to minus square root of x plus 1. And you can also think about the domain of this function. Remember, the domain is pretty simple. Your x plus 1 should be non-negative, so x plus 1 should be greater than or equal to 0. So I will be able to say that x is greater or equal to negative 1. If I do the number line, then my x's will start at negative 1, but must be greater than afterwards. So the domain of this inverse function is going to look like negative 1 closed infinity. The next set of examples we're going to execute as the things we have already talked about previously using those information. A relation in x and y is given. Determine if the relation defines y as one-to-one function of x or not. So what you are looking for, the outputs. Negative 5 has exactly one input. 2 has exactly one input. 1 has exactly one input. 4 has exactly one input. So all the outputs have exactly one input. So it is 1 to 1. How about the next example? See, 1 has one input. 3 has one input. 4 has one input. Negative 2 has one input as well. So again, all the outputs, 1, 3, 4, negative 2, has exactly one input. So 1 to 1 or injective. Graphically, if you look at this thing, 2 has exactly one input. 2's input is 13. 3 has exactly one input and the input is 25. 4 has exactly one input, the input is 25. But I still cannot call it 1 to 1. Why I can't call it 1 to 1? If you think about number of outputs, 25 has more than one outputs. So it is not a function. I asked you to check whether they are one-to-one function or not. You first find whether it is a function or not. It is not even a function, so no question of being one-to-one function. I am not going to even check for one-to-oneness if I'm not a function. If I look at the second example, I will find out it is a function because 2 as an input has exactly one output, 3 as an input has exactly one output, 4 as an input has exactly one output. But is it one-to-one? It is a function, but is it one-to-one? Well, now check from the perspective of outputs. 13 as output has exactly one input, 2, but 25 as an output has two inputs. Both 3 and 4 are inputs for the output 25. So if the output is 25, it has two different inputs, 3 and 4. So it is a function, we agree with that, but it is not one-to-one. Let's do a couple more examples of this type. So we'll carry on page number 9, and these are graphical examples. We're trying to understand, are these one-to-one functions? So see, it doesn't matter where you want to draw the horizontal line, you will be crossing the graph in exactly one point. So I get to say that this function is 1 to 1. But then the next graph, I'm failing the horizontal line test. I have horizontal lines that will cross the graph in more than one point. So it is not 1 to 1. Similarly here, you can think of horizontal lines that will cross the graph in more than one point. So not 1 to 1. As usual in this one, I can think of horizontal line that will cross the graph in more than one point. So I will say not 1 to 1. We'll do more examples. This one is not 1 to 1 as I'm crossing the graph by a horizontal line in more than one point. So it is not 1 to 1. The next picture, I don't even check for horizontal line test. Why? Think about the vertical line test first. You are crossing the graph in more than one point using the vertical line. So not even a function. To start with, it is not even a function. So why even bother to check for the one-oneness? Not even a function, cannot be 1 to 1. So we'll just be a little careful when we're taking one-oneness. First check whether you are a function or not by doing vertical line test. Similarly, this example, you have a y-axis crossing the graph in 4 different points. So I will go ahead and say that it is not even a function. So not 1 to 1. Now we will check one-to-oneness of functions that are given in algebraic form. So we're going to use the algebraic characterization of one-to-one function. Remember my process. I said given the function, you are checking whether it is 1 to 1 or not. Start by saying f of a is equal to f of b and trying to establish the equality between a and b. So let's see. I will get 4a minus 7 for f of a, 4b minus 7 for f of b. Then I can add 7 on both sides and I will end up having 4a equal to 4b. I can divide both sides by 4 and I will have a equal to b. So I'm successful in establishing a equal to b. Answer is 1, 1 function. So injective function. And I will go ahead and say that yes for one-to-oneness, as the instruction in the question is asking you to y or m. The second function is a square function. And I'm going to start again by saying f of a is equal to f of b. And remember what happens. You get a square minus 4 equal to b square minus 4. Same treatment. You add 4 on both sides. You get a square equal to b square. You're trying to get a equal to b, so I would rather take square roots on both sides. The left hand side will be absolute value of a. The right hand side will be b. So I will get a equal to b or a equal to negative b. You wanted this, but you got this as well, which makes it not 1 to 1. Remember, I wanted to show that it is giving me a equal to b, but instead I got a equal to negative b as well. So I would say that the function is not 1 to 1. You can think about the graph of the function real quick. It will be the graph of the parabola shifted 4 units down. So that point here is going to be 0, negative 4. And see, I'm failing the horizontal line test. I'm crossing the graph in more than one point. So it is not 1 to 1, both algebraically and graphically. Fx equal to absolute value of x. So I will first go ahead and show you that if you say fx equal to absolute value of x in the graph, it is the v that is centered at the origin. And I'm clearly failing the horizontal line test because I'm crossing the graph in more than one point. So it is not 1 to 1. How do I know algebraically? Start by saying f of a equal to f of b. So absolute value of a is equal to absolute value of b, which will give you two solutions, a equal to absolute value of b or a is equal to negative absolute value of b. This one will give you two solutions, a equal to b or negative a equal to b. This one will give you two solutions as well, a equal to negative b or negative a equal to negative b. But if you think of all four of these solutions, this one is a equal to b, this one is a equal to negative b, this one is a equal to negative b, this one is a equal to b. So I essentially have only two of these solutions, but I still have a equal to negative b along with a equal to b. So I did not get a equal to b by itself. I got a equal to negative b as well. So it is not one-to-one algebraically. Fx equal to x squared plus 1. Let's see the graphical nature of this function. X squared plus 1 is the graph of x squared shifted up by 1 unit. Still fails the horizontal line test. Can't be one-to-one. But we will check it using the algebraic approach. So write f of a equal to f of b. So you get a squared plus 1 equal to b squared plus 1. Subtract 1 from both sides. You get a squared equal to b squared. Take the square roots on both sides and you get absolute value of a equal to b. So I get two solutions, a equal to b or a equal to negative b. Again, I did not get a equal to b by itself. I got a equal to negative b as well. So even algebraically, I have established the function is not one-to-one. The final one is fx equal to square root of x. And I'm going to do my same testing. I will start by saying fa equal to f of b. So square root of a is equal to square root of b. To go to a or to b, I will square both sides. And if you square both sides, you get square root of a to the power 2 equal to square root of b to the power 2, which will imply a is equal to b. And hence I get to say this is one-to-one. And recall the graph of fx equal to square root of x. That's one of the parent functions. It is this way. And see how my horizontal lines are crossing the graph in exactly one point, giving me the one-to-oneness using graphical approach as well. For the next couple of examples, we are given with two functions and we're trying to understand whether they are inverses of each other or not. How do you know they are inverses of each other or not? Do f composed g should be equal to x? Do g composed f should be equal to x? So let's try to do that. It's just practicing composition of functions. So when I do f composed g of x, by definition this is f of g of x, which is f of x minus 4 over 5. Now f is 5x plus 4. So I write 5. In place of x, I write the input x minus 4 over 5 plus 4. Clearly 5 and 5 will cancel and I will get x minus 4 plus 4, which is x. So one side is good. F composed g is indeed equal to x. How about the other side? G composed f of x. This time f is the inside function, so g of f of x. I will say g of 5x plus 4 because f of x is 5x plus 4. Look at g. G is x minus 4 over 5. So you write 5x plus 4 in place of x minus 4. So this is the x part. X minus 4 over 5. Clearly I can cancel the 4's and get 5x over 5, which is x. So both of them, they satisfy each other. I get to say these two are inverses of each other. Let's do it with h and k. So again, you are going to do h of k of x, and you will get h of x plus 3 over 7 which is 7 times x plus 3 over 7. So 7 and 7 will cancel, and I will get, and I forgot the minus 3, I'm so sorry. So if you look at your h is 7x minus 3. So it will be 7 times x minus 3. Then you cancel the two 7s. You get x plus 3 minus 3, which is x. So one side is good. The other side, which is k of h of x, will be equal to k of h is 7x minus 3. So now look at k. K is x. In place of x, you write 7x minus 3. Then you have plus 3 all over 7. So 3 cancels. I get 7x over 7, and that is equal to x. So again, I get to say these two, h and k, are inverses of each other. W and z. Let's do w of z of x. So z is inside. So that is w of 6 minus 2x over x. I look at w. It is 6 over x plus 2. But in place of x, I use the input 6 minus 2x over x. That wants you to find the common denominator. 2 is 2 over 1. So you multiply x on top and bottom to get the common denominator x. And you get 6 all over 6 minus 2x plus 2x over x. So I get 6 over, see these 2x's canceled. You got 6 over x. Dividing by a fraction means multiplying by the reciprocal of the fraction. So 6 times x over 6. I can cancel the two 6's and I will get x. So w compose z of x is x. How about z compose w of x? It will be z of w of x is 6 over x plus 2. I look at z. Z is 6 minus 2 times x. And your x is the input 6 over x plus 2. All over x again. So you write 6 over x plus 2. As in the last one, I will write 6 as 6 over 1. And then I multiply x plus 2 both on top and bottom to get the common denominator x plus 2. Let's see what happens. I distribute the 6, I get 6x plus 12. Then I distribute this 2, I get minus 12. And in the denominator, I write x plus 2 only once because I have the common denominator in both of them. I write it only once. All over 6 over x plus 2. Those two will cancel, positive and negative 12. And you will get 6x over x plus 12, x plus 2, all over 6 over x plus 2. Again, dividing by a fraction means multiplying by its reciprocal. So you get 6x over x plus 2 times x plus 2 over 6. So the x plus 2 terms, being top and bottom and being the same factor, will cancel. You can also cancel the 6 from the top and bottom and see what you are left with. It's x. So both composition has given you x. Hence, I will say w and z are inverses to each other. These two functions are inverse functions to each other. Our last problem in this handout is a cube root function, and we want to know the inverse of this thing. Instead of using fx, I'm using kx, but the process is pretty similar. You replace y for kx, and you get cube root of x plus 8. Then you interchange the variable, so you get x equal to cube root of y plus 8. You're trying to solve it for y. So you are going to cube both sides, or take the third power on both sides. So you get x to the power 3 equal to cube root of y plus 8 all to the power 3. I get x cubed equal to y plus 8. Then I subtract 8 from both sides, and I get x cubed minus 8 is equal to y. I have solved it for y. So the last step is writing the inverse. Instead of writing f inverse, because my function was k, I will say k inverse of x is equal to x to the power 3 minus 8. And that would answer my question. So I'm going to stop here and I will let you work on your own on your homework problems in TOPATH. If you have any question, please email me and I will get back to you as soon as I can.